All right, so I'm going to show you my final project. This is for ESN 260, and the first thing we need to show is that it works. You don't know what it is yet, but let's explain. It's a speaker. We have a potentiometer that's going to tell us the pitch of the speaker, and then if and when we press this button, it'll play a pre-programmed song. So here it is. It has 2 octaves of range. Okay. And then if we press this button here, I have it programmed to play the intro to Canon in D. And then whenever the song's done, it goes back to using the potentiometer. Then if you really want to have fun, you unplug power and ground from the potentiometer and it'll just make music based off of what it wants to do. Anyways, let's kind of show you how this code works. So there's 2 main files, which I have pulled up at the same time here. So this left file is the program itself. So we have a pretty simple setup. I'm setting up a BPM, so you can see how fast this changes here. You see how short those notes are? That's determined by the BPM. The higher the BPM, the shorter those notes can be, since that's why we have such a high BPM there. I set the button to work, which is this pin mode here, and then I have enabled interrupt for that port. Then we configure the speaker, the ADC, and we say we start a software DAC. So you can see there's quite a few more notes that I've commented out, just give it that 2 octave range instead of trying to go for 3, because the potentiometer has limited range and I'd rather have full 2 octaves than a couple extra notes. So based on the potentiometer input, it'll display a note if it's in between those things. Lots of if and else statements there, and then it'll close, and then it repeats. So this is the potentiometer code. And then here is our interrupt code. So anytime an interrupt happens, we reset the BPM just in case. I had something that switched the BPM before. Debounce the switch, and then we play this song. So right now, you can see how it starts slow and then goes fast. That's determined by the duration here. And you can see the notes on the left for each of these play statements. So let's kind of understand what those play statements are and what that's all doing. And that's in here, which is the header file or the driver for this. So the first thing that the header file does is it explains, oh, there's a ton of notes, and here are all of them. It's a lot more than we actually use, but it's something I found in the files from this guy, who did a lot of Arduino code for basically the same thing, although he used an actual DAC for it. Defining input-output, things like that for the programs over here, so it'll be a lot easier to use. This is the clock speed of the timer, which allows me to know the actual frequency. I have a duty cycle, so it creates a square wave whenever you're using timer A, because it turns it off and then on and then off and then on very quickly at a specific frequency. And then so here we have the ADC, which I just configured in one line, which is just really simple. I have it select port 4.7 as my ADC in. You can see that on the hardware. That's that brown wire right there, right here. And then we configure our speaker, which resets the timer, sets up how it's going to reset, and then sets it to be out for this pin, and also puts the beats per minute into the header. Driver, same difference here. Then we have that play function that we used a lot over here. So what that play function does is it sets the period, because you can't set frequency directly. I just use clock over frequency because otherwise I get a frequency that's closer to the clock speed. And so I wanted to have it be real frequency. So whenever you enter a frequency here, it is 30 hertz. You will get 30 hertz out, even though the clock speed's a lot faster than that because of this time rate clock over frequency. It's not perfect, but it's pretty close. Then we set the period and we set the duty cycle, which is what I just talked about earlier. It's half on, half off. And then delay by duration. So this sets the timer to go at that frequency and stays in this function until the note can be done. And so that allows this to not have to have a bunch of delay functions in here. It's built in. And then we have the delay duration function, which is a pretty simple way to have it stay within the BPM. I have a number that I just calculated by trial and error and a couple things on a calculator to say this is how long a beat per minute at this speed should be. So basically that's the clock speed over frequency. Again, it's the same kind of thing, just augmenting computer time versus real time. Then here is from Lab 11. This is a lot of code to deal with my ports. So that sets up inputs and outputs so I can write. And that's the end of my header. So all in all, what this does is we're taking the potentiometer output and we're converting it to a note. And so you'll notice it's kind of uneven. If I move evenly, and I didn't change the speed that I moved my hand, it's because the frequencies are very uneven. As you get higher, the frequencies are different and they're farther apart. So that's something I would like to do better in the next iteration. But for now, I can make a working song. And then that button, you could have more buttons, you could put in more things. And then here is what it does without power and ground here. It makes its own music, which is kind of fun. Anyways, thanks for watching. I know it's a bit long, but there's my video.